Ladies and gentlemen, I welcome you again to Simplified RSA, the guys who makes it looks easy, your number one learning channel. Today we are moving to chemistry, and our selected question for today, I'm just gonna present it here. So like we normally do, we select previous question papers which students may find to be challenging, and then we answer the questions live. So this is our selected question for today. This one is a bit more interesting because I believe it relates to stuff that we might have seen or witnessed in reality at some point in life, not if not every day. The question is about liquids boiling in a way. So the question reads, the vapor pressure versus temperature graph below was obtained for four unknown liquids. So we don't know what these liquids are. So we have liquid A, B, C, and D. And we are told that atmospheric pressure is measured as 101.3 kilopascal. That is the most important part of the whole scenario, atmospheric pressure. Why so? Because we have a vapor pressure versus temperature graph, and then they gave us atmospheric pressure. I'll show you how it works. Without wasting time, question 3.1, they want us to define the term boiling point. The term boiling point. In most cases, like I say, I feel like students may relate to these situations because you have seen water boil before, or you might have seen any other stuff boil. You have cooked something before whereby there was a boiling of some sort happening. So everyone is familiar with what boiling point is until we have to give a definition in an academic world in order to obtain marks, and then everything becomes like a total foreign concept. So now, the interesting thing that I've realized whenever I ask students what a boiling point is, they'll tell you that it's a phase where water boils, or some would say it's a temperature where water turns into gas, of which those are interesting answers that leads to someone assuring that someone does understand the concept indeed. But here's something that I want you to understand. Let me explain something first before I give the definition. So ideally, here is a situation where I want to demonstrate boiling point, right? This is a pot. Inside the pot, we have water as our content, and this is our stove, and that's the heat applied to the pot for us to end up resulting as with the water boiling, right? Let me close the cap. Let me put a closing cap here so the water is closed, so the pot is closed. As temperature rises, obviously inside the pot, the molecular bonds would be broken such that particles are going to start to move. They're going to start to move, creating vapor pressure inside the pot. So the black arrows would demonstrate vapor pressure of some sort moving around. But what I want you to understand is when there's vapor pressure inside the pot, externally outside the pot, we have atmospheric pressure as well that is exerted on the pot. And the atmospheric pressure will be constant in that case. In our question as given, our atmospheric pressure is 101.3 kilopascal. So that atmospheric pressure is being exerted on the pot, whereas inside the pot, as the temperature rises while the molecular bonds have been breaking off, and the pressure is increasing, the vapor pressure is increasing inside the pot. The water won't boil until the vapor pressure inside the pot, the vapor pressure inside the pot has to be equal to the atmospheric pressure externally for the molecules, for the particles of the water to give up and start boiling. So boiling point only occurs when atmospheric pressure externally equals the vapor pressure internally. That's when boiling starts to occur. So what I'm saying is, so what I'm saying is, whenever you get to define a boiling point, don't just say it is a temperature at which water changes to gas. Try to mention the vapor pressure and the external atmospheric pressure, because At the point where the vapor pressure equals the atmospheric pressure, that's when the liquid inside starts to boil. So it would be the right way to answer 3.1 by saying boiling point is the temperature at which the vapor pressure of the liquid is equals to the external atmospheric pressure. That would be the right way to answer 3.1. So that's it with 3.1. And then moving to 3.2. Now, moving to the next question, we have to use the information given in the graph to answer the question that follows. And then 3.2, we have to write down the boiling point of liquid B, and so forth and so forth. Okay, one question at a time. Now here I have this graph. I have our graph. Here is our given graph here. Now let's take a closer look at our graph. Ne? And now we know the definition of a boiling point. We know that boiling point is a temperature at which the vapor pressure equals to the atmospheric pressure. And we are given the atmospheric pressure here represented by the dotted line. This represents our atmospheric pressure, as everyone can see. Now, we can tell that the boiling point for each and every liquid is where is the temperature at which the vapor pressure is equals to the atmospheric pressure, meaning anywhere here. This is the boiling point for liquid A. This is the boiling point for liquid B. This is the boiling point for liquid C. And this would be the boiling point for liquid D, because at that instant, that's when the atmospheric pressure is equal to the vapor pressure. And then for us to answer the boiling point of liquid B, looking at the temperature graph, it goes 0, 25. So meaning it's 0, 5, 10, 15, 20, 25. 25, 30, 35, 40, 45, 50, like that. So meaning the boiling point of liquid B is here, which in this case, it would be 80 degrees Celsius, because we can see it goes from 75 to 80. That means the boiling point for liquid B, it would be 80 degrees Celsius. So the answer for 3.2.1, it would be 80 degrees Celsius, the boiling point for liquid B. 3.2.2, we have to analyze the graph again to tell the liquid which remains a liquid at 115 degrees Celsius. So the liquid which hasn't boiled when we get to 100 degrees Celsius. Again, let's look at our graph. So now, looking at our graph, one can tell that it's 100 here, 105 is here, 110, then 115 we are looking at here. Now we want to know which liquid it's still a liquid at this temperature here. Now going up, liquid D, you can tell that liquid D, it's below here. Liquid D, it hasn't boiled yet. Everything is above the atmospheric pressure at this temperature, but then liquid D, it was still a liquid at 115 degrees. So that's the answer for 3.2.2. Liquid D will remain a liquid at 115 degrees. That would be the answer for 3.2.2. Now, 3.2.3, we have to investigate which liquid is most likely to be water. Which liquid is most likely to be water? Now, tell you what, a lot of students knows that water boils at 100 degrees Celsius. So we just have to investigate which liquid is closer to 100 degrees Celsius at its boiling point. Analyzing our graph, one can see that if I go to 100 degrees Celsius and I look which liquid boiled at 100 degrees Celsius, I would go 100 degrees and then I go up to where it touches the atmospheric pressure, and then we can tell that this liquid here, which is liquid C is likely to be water because it boiled at 100 degrees Celsius. So that's the answer for 3.2.3. And then 3.3, we are required to state the phase change that takes place at the stage when the vapor pressure is equals to the atmospheric pressure. A giveaway. If we have to state what happens where the vapor pressure is equals to the atmospheric pressure, obviously the liquid boils. So it's either you answer and say the liquid boils, or you say the liquid evaporates. You would still be on the same answer, because the moment the vapor pressure equals to the atmospheric pressure, liquids gets to boil. That's the definition of a boiling point. Anyway, 3.4, what happens to the temperature of a liquid during a phase change? Write down only increase, decrease, or remains the same. Let me tell you something interesting. Let's go back here. As the heat hits the pot such that the molecular bonds are broken down, and then there's a vapor pressure increase inside the pot until to a point where the vapor pressure is equal to the atmospheric pressure. As the change happens, the temperature remains the same. If we were to put the thermometer inside there, the temperature would remain the same at that boiling point as the change takes place. So if the boiling point is 100 degrees Celsius, the temperature would remain 100 degrees Celsius as the change occurs inside that pot. And now, the next question brings us to the explanation as to why. So now, because when the change is happening, the intermolecular forces are broken down, and the energy that is used to break down the intermolecular forces has reached its goal to result in phase change from liquid to gas of the liquid that is inside there. There is no more energy available to increase the kinetic energy of the particles inside the pots, because the change is already occurring. So energy is being used to overcome the intermolecular forces inside. There's no more energy remaining to for the kinetic energy. There's no more energy remaining to can break even more particles, such that whenever you put a thermometer there, the temperature will still remain the same. So that's our answer for 3.6. That's our answer for 3.5, I mean. And then 3.6, and then 3.6, we are required to tell which liquid A, B, C, or D has the weakest intermolecular forces. And we have to give a reason for the answer that we choose, for the liquid that we choose. I would say the liquid that has the least boiling point, like the liquid that boils at the lowest temperature, is the one that has the weakest intermolecular forces. So let's analyze our graph again. Obviously, it has to be liquid A, because liquid A, it was boiling already at 55 degrees Celsius, meaning the bonds were easy to break. There is our boiling point for liquid A. This is it here, meaning the intermolecular forces, the intermolecular particles for point A were easy to break, such that it was boiling at an earlier stage. By 55 degrees Celsius, it was already boiling. So that's our answer for 3.6. Now, question 3.7. What is the relationship between vapor pressure of the liquid and temperature? To tell the relationship of the vapor pressure and the temperature, you can observe again from the graph itself. As the temperature increases, the vapor pressure also increases. So our temperature increases from this direction to that direction, and our vapor pressure increases from this direction to that direction. And then you can tell the behavior of the water. As the temperature increases, the vapor pressure also seems to be increasing in that order for all the liquids, which means that vapor pressure is directly proportional to the temperature. As temperature increases, the vapor pressure also increases. So that would be the relationship for 3.7. So to answer 3.7, you just have to say, When temperature increases, vapor pressure also increases because temperature is our independent variable. When temperature increases, also the vapor pressure increases, or just by saying vapor pressure is directly proportional to temperature, it would also give you the full mark for 3.7. The most interesting thing about chemistry is that it relates to stuff that we know in reality. Like I say, this question is something which one might have observed at some point in life, like I say. So the secret here is just to study the notes, understand the concept. Otherwise, thank you for watching. If you've watched this far, please don't forget to subscribe to our YouTube channel, follow us in all our social media platforms, and you can contact us for private lessons on the number here. Send us a WhatsApp or send us an email. Otherwise, I'm Mr. Maimane. This is Simplified RSA, and we are the guys who makes it looks easy for you.